Right. So today's session is on laws of thermodynamics. So basically, we will be discussing the first law, second law, and the third law, and the associated terms for these three laws. Right. So what we have done so far is last time we work on this pure substance. If you remember, pure substance. Then we work on these two examples, right? Not actually both examples, but we work on example number one, right? Then there's another example. Maybe I will try to make another video how to work on these examples and then post it so you can follow these things later on, right? So let me talk about the first law of thermodynamics. So what the first law of thermodynamics says is the change in internal energy of a closed system is delta U is equal to the heat added to the system minus the work done by the system, right? So we introduce something called internal energy, right? So we will discuss what is this internal energy is what is this is later on. So basically this equation says, so this is a state equation, delta U equal Q minus W. So the Q is the net heat added to the system and minus the W. W is the work done by the system, right? So that's how it's pronounced. Q here is the work net heat added to the system, and W is the work done by the system, right? So in this case, we have conversion. That means work added to the system is plus, whereas the work rejected from the system is minus, right? Negative, right? And also in the W terms, work done by the system is plus, right? Again, done by the system is plus, work done on a system, that means you are work done on a system is minus, work done by a system is uh, is plus, and work done on a system is minus, right? So for example, let's say you have a kind of an engine here, right? So if we have like Q in, right? This Q in, so this is plus, right? And if say you have Q out, right, or UT, so this is minus, right? And let's say you have another one, work out, W out. This one considers as the plus, right? Plus. And if we have work in, right, W in, that is minus, considered as minus. Okay, now this you have to remember these conversions, right? Because why we are doing like this is what we refer, what we want is a system to uh, to input heat energy and output work, right? What we desire, what we like to have is to get the work out of the system. For example, an engine, let's say a petrol engine or a diesel engine, uh, we add the heat. That means by burning fuel, we add heat, then we get the work out, right? Work out is plus, adding heat is plus, right? That's how this conversion comes, right? Okay, now let's we talk about the internal energy, right? So the internal energy includes the kinetic energy due to the motion of molecules, right? Internal energy means basically all the kinetic and potential energy. So when we go to microscopic level, there are translation energy, rotational energy, vibrational energy, and all of that energy plus and all the energy associated to forces between molecules. So there can be electrostatic forces, magnetic and gravitational forces, and all the potential energy, all the kinetic energy, and all the potential energy. The summation we normally refer as the internal energy, right? Include the energy related to microscopic motion and interaction of this system's molecule. That means we are going into microscopic level, right? That means we are not dealing it as a whole body. Now you are Now we are familiar with kinetic energy and potential energies, right? For example, let's say a car can have or maybe a rock, right? It can have a potential energy and kinetic, but we are not dealing with that level, right? That is not the level. We are going into microscopic level. We are talking about the kinetic energy and potential energy of microscopic level, right? So, and summation of all energy we refer as the internal energy, right? So internal energy is a state function, right? So it's a state function. What is mean by the state function is it is depend only on the state where it is right now. Right? It doesn't matter how he come to that state, right? Only depend on the state. Meaning it depend only on the current state of the system and not on the path taken to reach that state. Right? Doesn't matter how it's come to that state. Right? For an ideal gas, for example, the internal energy is functionally dependent on the temperature and the number of particles, but independent of pressure and volume. So, internal energy is only dependent on the temperature. It doesn't depend on the pressure or the volume or any other constant, right? So, only depend on the temperature. Right? So, that's mean if you increase the temperature, internal energy increases, and if you decrease the temperature, of course, internal energy decreases. I hope you remember the experiment that we have done. We had discussed last time the fire piston one, right? We what we do is we just make a piston, right, and apply a force here, right? Then put some cotton bud there and press it hard. Then it catches fire. So that's the fire piston experiment. So that's can you explain it using this law, right? Now, if we explain that experiment using the first law of thermodynamics, now there's no heat transfer, so this one equal to zero. Therefore, right, and we are doing work on the system, right? So work done on the system is minus, therefore what we get delta u equals q is 0 minus and minus w. Why minus w? Because we are doing work on the system. Doing work on the system is minus, therefore delta u equals, so we have minus minus goes off, then we get delta u equals w, right? Now what happened delta u, so what this means is all the work done on the system is converted as the internal energy. So the internal energy increases. When the internal energy increase means the temperature increases. So the temperature increases, then the temperature uh, due to that increased temperature, the whatever the things here, I mean the cotton bud, they catches fire, right? So that's how we can explain this one, right? Right. So internal energy. So can we measure the internal? So now this one is delta U. Remember, it's not just the internal energy. This is delta U, right? So difference of internal energy equals Q minus W. So can't we measure the calculate the internal energy? Yes, we can, right? So the internal energy of the ideal gas is determined by its temperature and is independent of volume and pressure under the ideal gas assumption. So the formula we can derive it like this: U equals N times Cv times T. N is the number of moles of the gas, Cv is the molar heat capacity at constant volume, and T is the absolute temperature in kelvins, right? So let me talk about the Cv value. So the Cv value for most of the monatomic ideal gas, that means it contain only one atom like helium and neon. Cv is normally taken as 3 by 2 over R. R means the gas constant, right? And for diametric gases like nitrogen and oxygen, and Cv is taken as the pi divided by 2 into R, right? Likewise. So we can have different values for different gases. Right? So let me work on a small example. Now this is uh, example. So let's say you have 2 moles of diatomic nitrogen at a temperature of 300 Kelvin. Assuming Cv equal 5 divided by 2R for diatomic gases, calculate the total internal energy. So it's a simple substitution. So N is 2, right? Because we have 2 moles, right? And Cv is equal 5 divided by 2 uh, multiplied by 8.314 gas constant, and the T is temperature 300 Kelvin. So it becomes 12,171 joules, right? So the U internal energy measured with joules, right here. So sometimes we call kilojoules or like this, right? Sometimes we refer specific constant. That means divide by the mass, then we get kilojoule per kilogram, right? Okay, kilojoule per kilogram, like this, right? If you refer the our tables, you will find this most of the times kilojoule per kilogram. Okay. Then there's another example, example number 4, and I'm not going to do it in here. It's basically heat transfer question. What I want you to do is try to work on this one, right? So what this basically do is example says during steady state operation, a gearbox receives 60 kilowatt of power to the input shaft and delivers power to the output shaft. For the gearbox as a system, the rate of energy transfer by convention is given in this equation, and all the values are given in here, right? So how we can approach this one? So I want you to stop this video and try to work it on this example, and later on you can check with the answers, right? So how we can start with this one is using the first law of thermodynamics. So we can write delta U equals Q minus W, right? Okay. Uh, because this is steady state, therefore this one equal delta U equal to 0. Therefore we can write 0 equals Q. Basically the uh, Q is the heat transfer, right? Heat transfer, and W is the work. Since we have given the rates, right, 60 kilowatt, right? And the Q dot here, so we can say this one as Q dot minus W dot, right? So this is our gearbox, right? So we have W dot in, and we have W dot out, and also we have Q out, Q dot out. So this is how the diagram should look like, right? Then Q dot you can find using this equation, right? H is given, A is given, TB and TF all are given. It's just a simple substitution. So you can find the Q dot, and then the W dot equals to Q dot in minus Q dot out, right? So let's we write the W dot. So the W dot here is Q in, which is minus, right? That means minus 60 kilowatt minus whatever the W dot out, right? Then if you substitute this equation in here, let's say this is A, then all the unknowns, the unknown is only the W dot out, right? Then you can figure it out what is the W dot out. Right? That's how we can work on this equation, right? So this is again a very important concept we call the enthalpy, right? So the other properties such as internal energy, pressure, specific volume, and temperature, enthalpy also a property which present as the sum of the internal energy and the pressure volume products. So enthalpy we normally denote as H equal to U. U is the internal energy, and the PV, product of pressure and volume, right? Now, don't try to find out what is this enthalpy, and I don't understand this one, and I need to look it out. What is this enthalpy likewise, right? Because this is all the things you need, right? These all the things you need, right? So enthalpy is a measure of a total heat energy, right? So basically a measurement of the total heat energy absorbed or released in a thermodynamic system, right? That's all the things you need, right? Likewise, the internal energy, pressure, and specific volume. This is again enthalpy, also again a property, and and it's equal to U plus P. That's the all the thing you need to know, right? Okay, right. With that, we can come to the second law of thermodynamics, right? So, of course, since enthalpy is equal to U plus PV. The unit for this enthalpy also in joules, right? Because the internal energy measured in joule, therefore enthalpy also measured in joule, right? When we come to second law of thermodynamics, there are several statements for this one, but we are particularly interested on only two statement. They are called Clausius statement and Kelvin Planck statement. Right? So let me go one at a time. So what the Clausius statement says is that it is impossible for any system to operate in such a way that sole result would be an energy transfer by heat from a cooler to a hotter body. Right? Now, I'm sure it doesn't matter how many times you read this statement, you will not get what this mean. So let me try to figure it out. What this basically mean is you have a hotter body. So this is the hotter body here, right? So right, you have the hotter body here, and you have the colder body. So the natural way of transferring heat, of course, from the high temperature to the lower temperature, right? So that is the natural way of transferring energy. If you have some kind of connection between hot and cold, hot body and cold body, then you have a natural way of coming heat from a hotter body to a colder body, right? So what this mean in this law is it is not possible to transfer heat from colder body to hotter body unless you have done some work on it, right? So that means you can transfer heat from colder body, that means from here to here, colder body to hotter body, but you have to input work, right? Otherwise, you can't do this. That's what basically it means, right? The natural way is this, of course, that you know. Other way also possible. That means you can transfer heat, absorb the heat from colder body, and then dump into the hotter body, but it will involve work. Right? This is what exactly happened in air conditioning. Air conditioning or freezer or the uh, refrigerator. That means absorbing heat energy from the colder body and dump into hotter body. Right? That's what this statement says. So that is the Clausius statement. Then we move on to Kelvin Planck statement. What the Kelvin and Planck said was, it is impossible for any system to operate in a thermodynamic cycle. So it is a thermodynamic cycle and deliver a net amount of energy by work to its surrounding while receiving energy by heat transfer from a single thermal reservoir, right? Again, let me try to break these things up, right? So you have a heat source, that means you have a hot body. You have heat sink, that means colder body. Heat source means where the heat is supplied, and the heat sink means where the heat is absorbed. So if you so you have a heat engine here, some kind of a device, right? That means what is the heat engine is? Heat engines mean basically convert the heat into work, right? What this mean is it is not possible to convert the heat energy 100% into work. That's what this means. Okay, that means you should have some kind of waste, right? Some kind of a uh, waste to the heat sink, and only a portion will be converted into work, right? That means uh, if you absorb 100 unit, you won't be able to convert that 100 into 100%ly that unit into work. There always will be some kind of a waste which goes to which dump into heat sink, right? That's what is mean, right? Okay. That means you can't convert 100% heat into work. That's the other way, right? There are always a loss, right? That's why you take the popular engines like for petrol engine and diesel engine. You can't convert 100% heat into 100% work, right? So I want you to search what are the efficiencies. What are the efficiencies of normal petrol engine and diesel engine? Then we can discuss later on uh, why it is not why we can't achieve 100% energy conversion in any of these engines, right? Okay, so this is basically a combination of the process statement and the Kelly class statement. So you have the hot reservoir here. So the hot reservoir here, okay, and so yes, you have the high temperature here, hot reservoir, and you have the lower temperature reservoir. And normally, what it do when it comes to when the heat flows from high to low, right? High to low, you can convert some part as the work, right? So you can transfer energy from heat from the lower to higher temperature, but it involves work, right? If this goes this way, you can get work out. If it this way, you have to input work, right? So there is the heat engine. We call this one as the heat pump, right? So heat, what the heat engine do is absorb the heat from higher temperature and dump into the lower temperature. While doing so, some portion will be converted into work, right? Then what the heat pump is, pumping heat from lower temperature to high temperature while involving work. Right? We call heat pump. This one called heat engines. Right? Don't worry, we will discuss about heat pumps and heat engine later on in more details. Right? So, for example, petrol engine is a heat engine. Uh, then we go diesel engine, petrol engine. Then all the thermal power plants are heat engines, right? Then refrigerators, air conditioners, freezers, all are heat pumps, right? Right. So then we come to another one of the important concept we call entropy, right? Again, likewise, the internal energy, enthalpy, then we have entropy. So we have internal energy, enthalpy, and the next thing is entropy, right? So all of these things are based on laws, right? Basically, the first law introduced the internal energy, second law introduced the enthalpy, and the third law introduced the entropy, right? As I said earlier, if it is given as the law, just remember it. Don't try to figure it out. Don't try to dive deep and search what this means. Right? Just take it as it is and memorize it. That's the all things you have to do. Right? Now let me talk about a little bit on what is entropy means. Is right. So, in thermodynamics, entropy is a fundamental concept that relates to the overall order or disorder of a system. Right? What entropy discuss is how the system is ordered, whether the system is ordered or disordered. Basically, higher entropy means there are much disorders in the system. Low entropy means there are less disorders. That means there are well ordered. System is well ordered. Low entropy means low entropy means system is well ordered. High entropy means system is disordered. Right? Right. The second law of thermodynamics states that the entropy of an isolated system tend to increase over time. Right. Okay. In other words, in natural process in an isolated system tend to move toward the state of higher entropy or greater disorder. That's mean in natural way, in nature, uh, what it happens is entropy is always increasing. We normally say the entropy of the universe is always increasing. That means the disorder level is increasing always, right? For example, how to remember this one? You let's say you make you arrange your room very nicely, right? Right. Let's say a classroom, or maybe you arrange your desks and chairs and books and everything very neatly and nicely, right? Then what happens over the time? Over the time, it automatically get disordered, right? So that's why we say normally things tend to get disorders, right? It's not automatically get ordered. It automatically make the things disordered, right? That's why we normally say the entropy of the system always increases. Entropy is related to the distribution of energy within a system. A system with low entropy has its energy distributed in an ordered or concentrated manner, while a system with higher entropy has its energy dispersed or spread out. Again, when you talk about the entropy in relation to the energy, if the system has low entropy, that means the energy is ordered. Energy is organized in ordered way, and the high entropy means energy is not organized in order; they are more dispersed or spread out. Right. For example, consider a container divided into two compartments with the gas confined to one compartment. Let's say you have a container which has two compartments, and one compartment is filled with gas, right? So since they are only low volume, they are compact, pressurized, therefore we normally say it has a low entropy. Then what we do, we uh, remove that divider. So we have divider, separate the two compartments. Then we remove the divider. Then the air has more room to flow. That means it has more randomness. That means it gains more entropy. That means higher entropy. Right? Okay. Entropy can also be interpreted in terms of the number of microscopic arrangement or configuration that correspond to a particular microscopic state. That means how many microscopic arrangement it has, right? Higher the entropy means it has lot of microscopic arrangement, right? And low entropy means is that less amount of microscopic arrangement. A highly ordered or structured arrangement correspond to a low entropy state, while a more disordered arrangement correspond to a higher entropy state. Right? Mathematically, entropy is often denoted by simple S and is related to the heat transfer Q and temperature of the system through the equation. Right? Delta S change of entropy equals to Q divided by T. Right? Okay. So, in contrast, entropy is a function of quantity of heat, which shows the possibility of conversion of that heat into work. Again, what is basically mean is uh, higher entropy. Now in Kelvin Planck statement, we talk about uh, in we can convert only a portion of the heat energy, right? Only a heat. So we have heat energy close here. Only a portion can be converted into work, right? Rest of the things we can't convert it into work, right? Only a portion can be converted. That is the law, right? You can't convert heat into work 100%. That's what it means. So let me combine this one. Let me draw a line in this statement with the entropy. So if you have ordered energy packets, if you have ordered energy, that ordered energy can be converted into work. If you have disordered energy, that disordered energy you can't convert that into work. will be dumped into the heat sink, right? That means if you have higher entropy means your disorders are higher. That means your energy packets are disordered. That means you can't get good work output. If your entropy is lower, then you can get more portion as the work output, right? Okay, right. So sorry about that. So let me continue on. And right. So yes, we are talking about the entropy. So in contrast, entropy is a function of quantity of heat, which shows the possibility of conversion of work of that heat into work. An increase in entropy is small when the heat is added at the high temperature and is greater when the heat is added addition is made at the lower temperature. Thus, for maximum entropy, there is a minimum availability of conversion into work, and for minimum entropy, there is a maximum availability for conversion into work. Right. So, I want you to read these things out, and you will be able to understand, I hope. And later on, if there is a question, we can discuss in the class. Right. Okay, so that is entropy, and then entropy change, right? So I hope you remember we discussed about few processes like isothermal process, isobaric, isochloric process, right? And we talk about the adiabatic process, right? So and we have another process here we call isentropic process, right? So an isentropic process is a special type of adiabatic process, right? So okay, what is an adiabatic process? That if there is no heat transfer, we call that one as adiabatic process, right? Only only work is involved, no heat transfer, then we call adiabatic process. So isentropic process is a special type of adiabatic process where there is no entropy change within the system, right? No heat transfer, we call adiabatic process. No entropy change, we normally call that one as isentropic process, right? So the entropy of the system remain constant throughout the process, we call as the isentropic process. Examples are compression and expansion of gases in an ideal compressor or turbine. So this is true for engine as well. If you get the petrol engine or diesel engine, so we have four stroke. If you remember, we have suction, compression, power, and exhaust. During the compression and the expansion, that's in power stroke, compression stroke, and power stroke, we consider as the isentropic process, right? So we will discuss those things in more details when we work on the cycles, right? Uh, for now, remember that the compression and expansion of the engines are basically considered as isentropic process. Right? Again, the nozzle flow, right? The fluid in fluid dynamic, converging and diverging nozzles we normally refer as the isentropic process. What do you mean? If you remember the nozzle, right? So you have flow, you have like this nozzle, right? So you have V here, V1 and V2. Normally, due to this cross section changes, we say V2 greater than V1. Right? So this what happened in here, this increasing speed, this process we normally refer as a isentropic process. Right? Again, idealized fluid flow in pipes also considered as isentropic process. Right. Then we have third law of thermodynamics. Now this is not very much important, right? Now we talk about the entropy. So this talk about the zero entropy, right? The third law of thermodynamics states that the entropy of a perfect crystal at temperature of 0 Kelvin, that means absolute zero, is equal to zero, right? Uh, again, you don't need to dive in much into this third law of thermodynamics, but I have given you a link. If you are interested, you can have look at this link. It's a YouTube video which explains the third law of thermodynamics. Okay, right. So far we have discussed about the zeroth law, first law, uh, second law, and third law. And are there any fifth law, fourth law, and fifth law? No, there is not, right? So that is all we need for this module, right? Okay. Then we have heat engine and heat pump, right? So right now we will discuss about heat engines and heat pumps. We will discuss later on, right? When we do the cycles, basically the refrigeration cycle, we will talk about the heat pumps. So let us discuss about heat engine. So the heat engine is a device or system that convert thermal energy into mechanical work. If any kind of a device that convert heat into work or heat into mechanical work, we call that one as the heat engine. All the engines like steam engine, petrol engine, diesel engine, all the thermal power plants are considered as heat engines, right? So there are four basic components of heat engines. There is the heat source that basically provide the energy. For example, it's a petrol engine. The heat source is the petrol. If it is a diesel engine, heat source is the diesel. Then thermal power plant. If it is a Novacoli power plant, heat source is the coal. If it is the Karavallapitiya power plant, heat source may be diesel, maybe naphtha, any kind of a thing, right? You have heat source, then the next thing is working fluid. The working fluid is there to absorb the heat from the heat source and do the work and do the expansion and compression, right? Heat source transfer the energy to a working fluid, which can be a gas or it can be a liquid. For example, in petrol and diesel engine, working fluid is atmospheric air. In most of the thermal power plant, working fluid is water. It's a liquid, right? Okay, right. Then we have expansion and compression. The working fluid experience expansion and compression cycles, which are often achieved through use of piston, turbines, and other similar mechanisms. Right? This process converts thermal energy into working of the working fluid into mechanical work. So this compression and expansion is what is used to convert the heat energy into work. Right? Then heat sink. After the expansion and work generation, the working fluid is tropically cooled down to down. Its energy is rejected to a lower temperature reservoir called the heat sink. Now, for example, if you get the petrol engine, heat source is the petrol, working fluid is air, right? Atmospheric air. Expansion and compression achieved using the pistons, cylinders, and pistons. And heat sink is again the atmospheric air because the rest of the energy, waste energy, will be dumped into the atmospheric air. So the heat sink is again the atmospheric air, right? Likewise, there are four components. Okay, and normally in heat engine we talk about efficiency, right? Because this is very we normally calculate the efficiency. We have because we are very interesting on the efficiency, right? The neta thermal is equal to W net, the work output divided by Q. Right? So this is the equation for the work efficiencies, right? Right. So with that, we can conclude this session, right? So the next session is about the Carnot vapor cycles. Now we are going to officially start the cycles, right? So we start with the Carnot cycles, then move on to Rankine, likewise, right? So what we are going to start from this onward is something like this, right? So we're going to talk about four cycles, right? Uh, if we had time, we will be talking about four cycles, right? So basically, we can we can divide into two categories, right? One is gas power cycle, the other one is vapor power cycles. In there, we have Carnot, right? Then we have Rankine cycle. In gas power cycles, we have Otto cycle, and we have diesel cycle, right? Now all of these are heat engines, right? Now this one is a heat engine, right? All of these are heat engines, right? And we have heat pumps, right? I would say cycles, heat engines. These cycles for heat engine. We have another one for heat pump. Heat pump. Under there, we will be discussing the refrigeration cycle. Okay. Now, we actually not work on lot on this Carnot cycle, but other four, 1, 2, 3, and 4. We will be discussing more of these cycles, right? Okay. So we will conclude this session for now.